So, in the previous class we have seen how to handle instabilities, specifically when the DC potential changes with time. Okay. Today I want to show you how we can handle solution resistance effects, especially potentiostatic measurements. Okay. Earlier we have seen in galvanized static measurements, solution resistance effects are easy to handle. Okay. Now we want to look how in case of potentiostatic measurements we can handle this situation. Okay. So, I want to show two examples. One is for a simple electron transfer reaction and second is for a two-step reaction with intermediate adsorbed species. Okay. And we will also go through an example code for this. So, some of this work we have published in 2012. This is a schematic illustrating how the potential drop occurs across this electrode electrolyte interface. If we have negligible solution resistance, we can say that all the potential drop occurs across the interface, and then we can model this with the circuit given here, that is AA capacitance in parallel with the Faradaic impedance. In case the solution resistance is significant, then part of the applied potential occurs across the solution and part of the applied potential occurs across the interface. So, you can say that the same potential drop as you measure or as you apply occurs, but then only part of it occurs at the interface. This del E in case of significant odd solution, the remaining potential drop occurs across this solution. So, we have to use a slightly different circuit, which is to add this R solution to this schematic or to this equivalent circuit representation. So, when we have this, what are the governing equations? In case of a simple electron transfer reaction, metal dissolving into the solution with a release of an electron, the current through this double layer capacitance is represented as I2A, current through this Faradaic impedance is represented by I2B, and of course, the current through the solution resistance is given as I1. Okay. Across the double layer capacitance, the current is given by capacitance multiplied by dE by dt, which is rate of change of potential with respect to time. And for the Faradaic impedance, we know how to relate this current to the potential. In general, we would write it as E. In this case, we would write it as E DC plus EAC, but that is only E occurring across this interface. So, we call this part as E2, we call this potential drop as E1, and the sum of E1 and E2 is what we apply. This case, this is a more general representation, and this is, we represent this as DC plus AC, but we do not mean that all the time the AC is a sinusoidal. DC is the average value, AC is any value that is fluctuating. So, if you measure E2, it might be sinusoidal, it might be another periodic pattern. We will say that this is E, this is T. The average value is what we would take as DC, and the value that is fluctuating we would call that as AC. And then of course, we have to employ Fourier transform to calculate what is the response at fundamental, what is the response at other harmonics, etc. Now, the I1 can be related to the E1 using the simple expression E1 by R solution is I1. E1 I can write it as E, that is the applied potential, minus the potential drop across this interface. So, whatever current that comes through the double layer and that comes through the Faradaic process, that sum of this, algebraic sum of this should be equal to the current that is passing through the solution. So, we can write I1 as I2A plus I2B. We have an expression for I1 written in terms of E2, we have an expression for I2A written in terms of E2, expression for I2B written in terms of E2. So, we can put them together, we have a ordinary differential equation incorporating the solution resistance effect. we know E, we control E, we do not know E2, we have to find the E2 value, we have to find the E1 value, so that we can estimate the I1 value. I1 is the current that is measured. Okay. So, we basically apply a DC bias and estimate the potential drop across the interface. We can only estimate, we can't measure it in the experiments. If we can minimize the solution resistance, we would just minimize it or eliminate it and then measure only the potential drop across the interface or control the potential drop across the interface. Since we cannot do that for whatever reason, we have to estimate it. So, if I apply DC potential and do not apply any AC potential, that means E1 is going to be constant, constant meaning it is going to be invariant with respect to time, E2 is going to be a constant. We can say that this goes to 0, d E2 by dt goes to 0, and the remaining terms can be solved numerically. It is an algebraic equation, nonlinear algebraic equation, but you can solve this and get the value for E2 DC. So, it is a nonlinear algebraic equation, you can use numerical method to get the E2 DC. So, as an example, K10 is 10 power minus 12 moles per centimeter square per second, B1 is 20 volts inverse, DC potential that we apply is 0.4 volts with respect to OCP, and we say that AA capacitance is 10 microfarad per centimeter square, all right. And what if the solution resistance is 1 ohm centimeter square? You can solve this, I am not showing you the code for this, but the value of E2 DC is going to be pretty much 0.4, it will not be exactly 0.4, but it will be close to 0.4. That means potential drop, most of it occurs across the interface. If we change the solution resistance to 100 ohm centimeter square, about 20 millivolts occurs across the solution resistance, 380 millivolts still occurs across the interface. If I make the solution resistance even larger, then you would see that more potential drop occurs across the solution. Okay. For a given case, given solution resistance, we apply a DC bias and on top of that we apply a AC potential, right. Now, we have to visualize the E2, the potential drop across the interface as a sum of DC and AC, but here I use the term AC in a loose fashion, it is not necessarily sinusoidal oscillation at frequency of omega. So, you can write the equation instead of E2, you can write it as E2 DC plus E2 AC, and this is what you would get. This is the potential that we apply, a DC bias plus an AC potential, and that is at the sinusoidal frequency omega. We control that. Of course, by definition E2 DC does not vary with time, therefore, that goes away. The remaining terms can be grouped, K10 B1 E2 DC can be written as K1 DC. This EDC and E2 DC can be grouped here, sin omega t and E2 AC can be grouped here. It is essentially a nonlinear differential equation. You can linearize this for a small E2 AC and solve it analytically, but practically we want to solve it for the cases where we have large amplitude perturbation. So, you have to use numerical method. So, if you have an arbitrary value, that is possibly a large value of E2 AC, you have to use numerical integration. Now, for a given set of kinetic parameters, right, if I apply a frequency of 100 kilohertz for a solution resistance of 1 ohm for a simple electron transfer reaction, the potential oscillations stabilize after some time. Earlier we have seen that when you have adsorbed intermediates, the current oscillations will stabilize after some time, right. Out here, even for a simple electron transfer reaction, if we have a significant solution resistance, when you apply a DC potential plus an AC potential, you will not get a steady periodic current response right away. it will drift a little and then stabilize after some time. Okay. In case of 1 ohm solution resistance, it takes maybe 0.05 milliseconds to stabilize. In case of 100 ohm solution resistance, it takes maybe 3 or 4 milliseconds to stabilize for this set of kinetic parameters at this DC potential. What that means is, how long does it take to stabilize? Depends on kinetic parameters, it depends on the DC potential, it also depends on the solution resistance value. It typically increases with solution resistance value, and if I have large solution resistance for same set of kinetic parameters, that means for the same reaction, this magnitude, if I just see this 100 kilohertz here as well as 100 kilohertz here, although I did not write it here, it is the same 5 millivolts AC amplitude and 100 kilohertz frequency. This oscillation is going from 0.3985 to 4015, this goes from 38051 to 38052, it means in fact it is much smaller than this scale. I just shown you the average here and the oscillations are shown in the inset. So, when you increase the solution resistance, the current oscillations are smaller, that is expected also. Now, how long does it take to stabilize? It is independent of frequency. It does vary with EAC 0 and it strongly depends on the kinetic parameter values, double layer capacitance values and the DC potential at which we acquire the data. Now, if I apply an AC potential, not all of that falls across the interface, a part of it falls across the solution. Now, how much of the EAC 0 applied actually falls across the interface? So, if I take the magnitude of E to AC and take the ratio of that magnitude to EAC 0, ideally I should get 1, all the potential that we apply should fall across the interface, and that will happen only when solution resistance is 0. Now, we can do the calculation for a variety of solution resistance values and for various frequencies. Okay. For one perturbation amplitude 10 millivolts, this is what we see. At low frequencies, it is more or less independent of the frequency. At high frequency, it is very small, and at intermediate frequencies, of course, it falls from high value to a low value, and ideal value is of course 1. When solution resistance is small, pretty much across this frequency region, it is more or less 1. When solution resistance increases, less and less applied potential falls across the interface and more of it falls across the solution. So, what fraction of it occurs across the interface, that depends on the frequency. At high frequencies, what happens is this: pretty much all the current goes through the double layer capacitance because it offers negligible impedance. When this impedance is negligible and this is anyway a finite number, you can say total impedance is more or less solution resistance. That means, more or less all the applied potential will fall across the solution resistance. When you go to low frequencies, this double layer capacitance offers very large impedance. So, most of the current will flow through this Faraday process. Faraday process, of course, the impedance value depends on the kinetic parameters, depends on the mechanism, depends on the DC potential, DC bias. And when this is comparable or larger than this, you would see most of the potential drop occurs across the interface. So, that is why at low frequencies, more of this applied potential falls across the interface. At high frequencies, it mostly falls across the solution. So, the way we would do this is apply a AC potential, wait for some time to get steady periodic response, and then in simulations we can record E2 as a function of time. Once you record E2, you can calculate E1 and then calculate the I1, that is basically calculate the current, and then apply Fourier transform, mark the current at omega fundamental as well as at 2 omega, 3 omega DC, any other frequency you want, you can calculate that and record that. You can calculate the magnitude of impedance as EAC 0 by I omega, here meaning the current at the fundamental omega, and the phase of course 0 minus 0 is for the potential, this is the phase of I omega. You can calculate the impedance. This essentially shows the equation relating E 2 to the I 1. So, as an example, 100 ohm solution resistance, EAC 0 is 100 millivolts, we can say wait time is 10 millisecond, we apply a DC potential, we set the kinetic parameter values and set the frequency range. We want to pass the kinetic parameter values as vector, and then first find the DC potential occurring across this interface, and we need to give that as the initial value for the integration. Okay. So, in this case I have used a function called f min bound. So, essentially what we do is to take the DC equation, which is I 1 minus I 2 A minus I 2 B equal to 0. I 1 is E DC minus E 2 DC by R solution. I 2 B Faraday current is F K 1 DC, and I 2 A is 0 because when you apply a DC potential no current passes through the double layer capacitance. Ideally this should be 0, I 2 B. So, numerically we want to calculate the residual and then take the square of that, that should become 0 or minimum here. And once you find the E 2 DC, use that as initial value and you have to integrate this equation, which is basically take this equation, rearrange it as d E 2 by dt as E minus E 2 by R solution minus F K 1, the entire thing divided by CDL. So, we retrieve the parameters, we need to use ODE 15s because it is a stiff equation. We find the value of K 1, we write the value of E. The first part we write it as E minus E 2 by R solution divided by CDL. Second part we write it as F K 1 by CDL, and this is the derivative. And after you integrate this, you can estimate the value of E 1, saying E 1 is E minus E 2, current of course is I, that is equal to I 1 is E 1 by R solution, and then the standard procedure of applying Fourier transform. So, we calculate the impedance at one frequency, we repeat it for a number of frequencies, you can get the spectrum. So, when you plot it, I can vary the R solution. I have tried 0.1 ohm centimeter square, after that 1 ohm, 10 ohm, 100 ohm, actually this should be ohm centimeter square. All right. When we plot normally, we will plot minus z imaginary by z real. That means 0.1 ohm would probably start here, 1 ohm would start somewhere here, 10 ohm would be much later, 100 ohm is going to be much later. In order to compare them, what I have done is, after calculating all the impedance values, I have subtracted the R solution and then plotted that in the abscissa. Ordinate of course, I keep minus z imaginary. So, what you see is the following: you can calculate this for small or large amplitude perturbation using this methodology, and you can calculate it for small solution resistance or a large solution resistance value. Now, when I increase the solution resistance value, obviously the measured impedance increases. What that means is, if I have a low solution resistance, I have a spectrum like this. If I have a large solution resistance, in the beginning we said it is just going to shift to the right. That is correct when you have an electrical circuit. When you have a reacting system, it is not just going to shift to the right, it is also going to change in magnitude. It is showing an increase here, it may not always be an increase. So, what it means is solution resistance is not just going to shift the impedance spectrum, it is also going to make changes to the values other than just adding our solution. But then it takes quite some time to do the integration and get the results, and it has to be done pretty much by numerical method for most of the reactions. There might be one or two exceptions, but by and large you will have to use numerical method, which means give a set of kinetic parameters given a solution resistance value to generate the spectrum. If you have an analytical expression in a computer, you can generate that in a second, maybe much less than that. If you use the numerical method, it will take probably half an hour or so. So, if you want to change the parameters and optimize, it is not practical to do in this method. This is the right method, but it is very time consuming. So, what we end up doing is we generate the spectrum assuming that the solution resistance is negligible, and then add the solution resistance. Although we know that that is not the best way, practically that is probably the only way we can do right now. If you are able to get an analytical expression, then we can use the correct expression, or if you get a faster code or faster computer, maybe we can try that. Now, what happens when you have an intermediate species? As an example, two-step reaction with an adsorbed intermediate, right. So, the same electrical circuit, equivalent circuit. The Faraday current, I would write it as f k 1 1 minus theta for this. Theta is the fractional surface coverage of the adsorbed intermediate, and k 1 is related to the potential as k 1 0 B 1 E 2. It is not k 1 0 B 1 E. Mass balance equation, of course, we have seen this before, it is gamma d theta 1 by dt. The first step forms theta, second step removes theta. So, you have k 1 and minus k 2, and the total current I 2 A plus I 2 B is I 1. So, earlier we have written this I 2 A as CDL d 2 by dt, we retain that. The second expression, because the reaction is different here, it is going to be f k 1 1 minus theta, and on the right hand side, of course, I 1 is related to the E 1 as E minus E 2 by R solution. Now, you can understand, you can write the DC expression for this, solve it, get the steady state value. In order to get the steady state value, we say this goes to 0, this goes to 0. You have two equations. Here k 1 depends on E 2 DC. So, we have two equations, two unknowns. We do not know E 2 DC and we do not know steady state value of theta. You can solve this. These are two algebraic equations, nonlinear equations, but you can solve them and then get the values of E 2 DC and theta SS. Use that as the starting point or initial value and integrate these two equations simultaneously. So, we have independent value as time, we have E 2 and theta 1 as the dependent variable, you have theta SS and E 2 DC as the initial points. So, you have to charge mass and charge balance equation simultaneously. Again, you have to see how long it takes for it to stabilize, wait for sufficient time and then take steady periodic results and record them. You get a value of E 2 as a function of time, theta as a function of time. We need only E 2 to calculate E 1 and we need only E 1 to calculate current. We do not need to use the theta, but we will have to integrate them together to get the value of E 2. And then we go through the same procedure, right, get the current value, apply FFT, get the ratio of potential to current and get the impedance. I am not showing you the code, I am just showing you the final results. This case, for this given set of kinetic parameters, you get two capacitive loops. When you change the solution resistance, here it increases, but I also want you to note the following. Okay. I have plotted different perturbation amplitudes. Here you can replot it for a given solution resistance, different amplitudes, and in all cases we have plotted real part of the impedance after subtracting the solution resistance. Now, increase in R solution causes an increase in the apparent value of RT and RP at any potential amplitude. Now, if I fix the solution resistance and replot this, so that I plotted only 5 millivolt and 200 millivolt AC, you can also plot the intermediate ones, but this is sufficient to illustrate. When you look here, when I increase the AC potential perturbation, charge transfer resistance seems to increase for this, it seems polarization resistance seems to decrease. At 100 ohm, charge transfer resistance increases, polarization resistance increases. So, what that means is, when you change the solution resistance, when you go to large amplitude perturbation, you do not always have a monotonic trend. Okay. Increase in EAC 0 causes non-monotonic changes in apparent RT and RP values. Some cases it looks like it is more or less same, some cases it looks like increases, some cases it might show a decrease, but it will cause a change. All that it means is, you can't just take a solution resistance and add it at the end. So, all this is done for potential static measurements, right. When solution resistance is significant, you can calculate the impedance response using numerical method. You have to use integration for pretty much any mechanism, and depending on the DC bias, depending on the kinetic parameter values, depending on the mechanism, depending on the solution resistance, the measured spectrum or simulated spectrum will change, and it is not always monotonic change even for the limiting values of polarization resistance and charge transfer resistance. Whether it is linear or nonlinear regime, RP NL or RP, it does not matter, you can't say that it is going to be monotonic. Okay. We have seen earlier that in case of galvanostatic measurement, it is actually a lot easier or simpler to model this. You just have to model the interface and then add the solution resistance effect later. Okay. So, it is a lot easier than doing it in the potential static measurement when we talk about simulations. In terms of experimental measurements, there is no extra difficulty in incorporating solution resistance effect. In fact, it is harder to reduce the solution resistance in some cases. Okay. We will stop here today.